Welcome to our video for Practice 1 in Activity 5. In this section of the activity, we are going to run a bivariate regression in SPSS, and we'll go through step by step how to interpret the results, including checking for the assumptions that are included in the SPSS output. We will create a regression equation from the results of the analysis, and then given specific predictor values, we'll use that regression to predict an outcome variable. The data that we are going to be working with in this spreadsheet is vertical jump and 100-meter sprint times that we've collected from a random sample. And our research question is identifying that we are interested in using the relationship between vertical jump height and 100-meter sprint time to be able to accurately predict trends in future fitness classes, 100-meter sprint times. So from here, we are going to go to our Practice 1 spreadsheet. And then I have a list of tasks that you guys will be doing in SPSS, and pretty much you're just going to follow along from this point on. Moving over to our data, the nice thing about regressions is we pretty much just copy and paste the data that we have in Excel. We don't have to reorganize anything. Everything should be set up as a parametric or scale type of variable. So if I pull up SPSS in my data window, I can paste the data with the variable names. We should see that the default is set to scale. However, if you just want to double check to make sure that your measures are appropriately labeled, you can change it to scale. From here, we will run the linear regression. So we go to Analyze, Regression, there we go, and Linear. And then from here, we can insert our independent and dependent variables. Recall that the dependent variable is the outcome that we are trying to predict. In this case, that's our 100-meter sprint time. And then the independent variable or predictor variables are going to be the variables that we are using to predict the dependent variable, in this case, vertical jump. Whenever we have a bivariate regression, the method or default method should stay as enter, since we are specifically or intentionally entering a single independent variable into our regression equation. Under statistics, you'll notice the default check marks are estimates and model fit. We want to also include some confidence intervals. You can click R-squared change for bivariate if you kind of just want to have a routine for what you click for linear regressions. You can choose R-squared change. This won't actually calculate really, or the calculations that we get won't be super meaningful because we don't have a bunch of models. Essentially, we're just going to have one model, so the R-squared change is going to be the total R-squared that we have for the vertical jump variable that we're putting into the equation. But if you want to click that, you can. We do want to include our collinearity diagnostics, our Durbin-Watson test, and then our case-wise diagnostics, which will identify outliers that are outside of 3 standard deviations. For plots, we will put our standardized predictive scores on the x-axis and our standardized residual scores on the y-axis, checking the boxes for our histograms and our normality probability plots. This will be our PP plots that we discussed in the lecture. So once we have our statistics and our plot set up, we can press OK, and we'll see that our output populates. Our variables entered and removed just show vertical jump using the enter method, which is exactly what we asked the output to do. Our model summary gives us our Durbin-Watson statistic, which is in fact between 1 and 3, so we can reasonably assume that we have independence of observations. Also within this model summary table, we can see our R-squared value, which is the shared variance, or rather the variance in our dependent variable that is explained or accounted for by using the independent variable. So if we wanted to do an interpretation of this, we could say that approximately 80.4% of 100-meter sprint time is accounted for by vertical jump. Okay. The ANOVA table is going to give us a p-value for an F statistic, which is evaluating how well our equation actually worked. So did using this equation give us a better prediction of 100-meter sprint time? According to this p-value, it is less than 0.05, so that indicates that we did have a significantly better prediction of vertical jump using this particular model. As far as our coefficients box, this will tell us how to build our equation, which we will do together. So if you recall, B is the coefficient column that we will use to build regression equations. The constant row is for B sub 0, or our y-intercept, and the following B coefficients that align with the independent or predictor variables that we stick into the model represent the change in the dependent variable for every 1 unit change in our independent variable. So in this case, negative 0.089 is basically telling us that we will decrease our 100-meter sprint time by 0.89 seconds for every increase in 1 inch of our vertical jump height. Okay, so we have a negative slope, meaning that as one variable increases, the other one decreases. Right, so we can use these B coefficients to build our equation, and I'm going to shift this over. In our equation, I'm just going to put an apostrophe and an equal sign. Reason being is that I want this to be copyable, but I also want to be able to see the equation full out. So if you usually put an apostrophe, it will read whatever you stick into your cell as text. So I'm going to put apostrophe equals, and then I will insert my B sub 0, or my y-intercept value first. So this was 13.028. And then I'm going to add. You can type this one of two ways. You can either put plus and then put your minus in parentheses, or you can just write minus 0.089 times some given x for vertical jump height, right? So given some vertical jump height, we can multiply it by this B coefficient, add it to the y-intercept, and then we should be able to somewhat accurately, predict 100-meter sprint time. Okay, so that's the equation that I'm operating off of, and we'll leave that there for now, but we will come back to it. Kind of further looking into our coefficients table, we can see the p-value for the t statistic that is responsible for looking at our b coefficient. So essentially this is the p-value for our b coefficient. P-values for our constant b don't really mean a whole lot, just because our actual x or independent variables don't have a value at the constant, right? That's when x is equal to 0. So we kind of can ignore the p-value in the constant row. For the p-value in the same row as our vertical jump, this is telling us that the slope, or this linear relationship that exists between our vertical jump and our 100-meter sprint time, is in fact significant in the population. We didn't touch on this too much, but we can also calculate confidence intervals for B. And the way that this works is very similar to how we would have calculated the true population mean for or using like a sample data. And what we're doing in this is we actually compare B plus or minus our t statistic, or critical value of t, times some standard error, which is listed here for our B coefficient. We're not doing these hand calculations this semester, but because SPSS calculates this for us, I still think it's a good thing to go through what this means. So based on our sample characteristics, you can see that negative 0.089 does in fact lie between negative 0.105 and negative 0.173. So using a 95% level of confidence, we were able to calculate this confidence interval, which tells us where, or kind of what range, the true population B coefficient, or where that would exist for vertical jump in relation to our 100-meter sprint time. If you want to look at how this makes sense in relation to the p-value, if our confidence interval does not contain 0, then we likely have a significant linear relationship, right? Because remember when we looked at the correlation coefficient R, when R was equal to 0, that was basically our null hypothesis, saying that there was no relationship. Although R and B are different from each other, they still kind of have a similar interpretation when the assumed value of B or R is 0, right? Because B is showing us a change in our dependent variable for every 1 unit change in our independent variable. And if we have 0 change in our dependent variable over 0 change in our independent variable, there is no relationship, right? Or if our slope is 0, essentially, the slope is undefined, or there is no correlation, right? So if our confidence interval does not include 0, then we likely have a significant relationship. If I scroll over, we can see our collinearity statistics, which is tolerance and VIF. I can pull up our criteria for these two. And remember that tolerance, or we assume that we do not have multicollinearity if tolerance is greater than 0.2 and if VIF is less than 5. So in our output, we can see tolerance is in fact greater than 0.2 and VIF is in fact less than 0.5. So we can reasonably assume that we've met our assumption that our data do not have multicollinearity. This should make sense because we actually only have one independent variable, and multicollinearity looks at when we have strong relationships between predictor variables. So if there's only one, then we kind of don't really need to check that. But it is good to know where this is and what values you're comparing tolerance and VIF to. All right, we're going to skip the collinearity diagnostics. We can see our residual statistics. We don't really cover this a whole lot in our output, so we'll skip over those. we can see here in our chart section our histogram that's looking at the regression of the standardized residual. The mean should be close to 0, which we can see is accurate in this little area over here. And our standard deviation is close to 1. These are two things that we do want to have as a characteristic of our histogram, in addition to our data relatively matching this normal curve, which for the most part it looks like we have accomplished. If we want to double check the normality of our residuals, we can look at our PP plot, which should show our residuals as blue dots, and we really want these blue dots to deviate as minimally as possible from this straight line in the center. And according to this visual representation, I would say that our residuals are relatively normally distributed. So our assumption of normality of residuals has been met based on these this PP plot and the histogram plot. The last plot that we usually need to consult for our assumption tests is for homogeneity of variance, and we can not homogeneity of variance. that's another week. Technically, homogeneity of variance isn't the wrong term, but homoscedasticity is what we're looking at when we have our standardized predicted values plotted against our standardized residuals. And what we should notice is that we have a linear trend. This can honestly be in any direction, but for the most part, we kind of want to see no pattern in the scatter plot that we generate. This indicates that we have a linear relationship, or likely have a linear relationship, and it also confirms that we've met our assumption that our data are homoscedastic. Okay, so from here, you guys can go to your answer sheet, and I've listed out some questions that you can answer. The last one that I want to do with you guys is doing the plug and chug for the estimated sprint times given vertical jump heights. So I've included this in your data spreadsheet, and the easiest way that we can calculate these is by using our equation that we've typed into Excel. I'm going to highlight this equation up to the apostrophe, and then I'll just paste it into this cell here and change the vertical jump reference to the jump height that I'm inputting into my regression equation. From there, I can literally just copy, and then I now have a predicted 100-meter sprint time based on relationships that I've investigated with vertical jump height. And that's it. Super easy. Okay, I'll see you guys in the next video.